All right. So, come back to this half of later half of this today's lecture. In the earlier half, I have defined what is the Zariski topology, and we now will define or will study some properties of this topological space. All right. The first one is, so whenever I use, for example, when I say plane curve, affine plane curve over K. This simply means your field is K and we are looking at VL of one polynomial in two variables. I will write it fxy. And this picture we are drawing it in L2. So, these are called affine plane curves over K. K because we know that this F is called the defining equations and that has coefficients in K, therefore, this over K. And we have seen some examples earlier that when is this infinite and when the complement is infinite. This I have done by using what I have proved is identity theorem for polynomial ring for polynomials. All right. Now, remember our goal is to study this topology with the help of ideals. This topology with the help of ideals. So, in other words, I am looking for a other way map. So, VL, this is a map from R ideals of Kx1 to Xn to A double F K algebraic sets. We have defined this map. This is a subset of power set of L power n. Any ideal A going to VL of A. Conversely, we define the map in the other direction. In fact, I will define a map from the power set of L, Ln to the ideals in the polynomial ring and what is the map? So, take any y is a subset of arbitrary subset of Ln and where do I map it? I will write its Ik just to remember that Ik of y. So, this is by definition. So, what is the definition? These are all polynomials f in Kx1 to Xn such that if I take f of any a, any y in y, this should be 0 for all y in y. Clear? I take all those polynomials which vanish on every element of y. So, a little example we write. So, example. So, let us take again y equal to, now I can write y equal to y axis. That means I am in n equal to 2 and if you like k equal to L equal to R in this case. Usually it is easier to take this case because we can draw a picture from which you can get an intuition. So, that means pictorially it is this and y axis. Now what is this set? Let us write down the definition. So this is IKY is precisely all those polynomials is now two variables, n is 2. So these are all those polynomials f in two variables x1 x2 such that this polynomial should vanish on every point in y, such that f of y is y axis. So that is here. So that means the x coordinate is 0. That means a comma a is 0. So 0 comma b is 0 for all b in y axis. So that is arbitrary element. So these are precisely, but obviously which is the polynomial here? For example, give few polynomials which have this property, namely one of them is x. So obviously the polynomial x1 belongs here. And any other polynomial, when I put x equal to 0, it is 0, that means there is no pure y term. See, this condition means there is f does not contain any pure monomial in y, because if it is there, then when I put b there, it will not be 0 for every. So therefore this ideal will precisely be generated by x1. Because all monomials in this all the polynomials in this ideal will have x1 present in every term. There is no term which is not present, where x1 is not present. So therefore this is precisely the ideal generated by x1. So one can calculate like that. Alright, now once you have a topology, so another thing I want to raise, so we have this, we have defined the map, this map, the name I will give is IK. And note that by definition of ideal, by definition this, so I will write on the next page, note that for every subset y in L power n, IKY is precisely the intersection y in y. So what is, I will write until, so this is my. Okay, now let us recall where we have y is in L power n, y is in L power n. So elements of y are tuples, small y in y are tuples, y1 to yn. So therefore, and this is my is precisely, remember my is precisely the ideal generated by x1 minus y1 xn minus yn, and these vanish on, this is the maximal ideal which vanish on the point y1 to yn, and everybody vanishes, so it is intersection. But the point to note here is a priori this is an ideal where the coefficients are in L. This is an ideal in L x1 to xn. But we want an ideal in IK. So we have to, this equality is not quite correct. So I would like you to think about this equality till at least couple of lectures, but definitely it is correct when L equal to K, because in that case this one. So, ultimately our aim is to, when we assume that the base field is algebraically closed, then these problems will not come, but then these problems will keep coming, and then we have to either modify our definition or find a remedy which will work in an arbitrary case. So, this will come with time and understanding. Okay, another issues I want to raise is when I say if I have a topological space, recall, these are all, because I am not going to do topological thing extensively. So, I will recall from a first course on a topology. If you would have done it, that will be good. Otherwise, we will have to recall this thing from the topological books, some basic books on topology, and I would suggest you should look at the general topology book, by Cayley. This is one of the good book, and it is the first course. You can find all the definitions which I have used there. Alright. So, what is a closed sets I already defined, they are the complements of the open sets, and whenever you want to give a topology on a set, you either give open sets or give a closed sets, that is equivalent, because you can get closed sets from the open sets by taking their complements, and you can get open sets from the closed sets by taking their complements. Alright. So, what is the closure of a subset? So, X is a set, and let us say tau is a topology on X. Now, what is a closure? So, if I have a subset Y of X, what is the closure of Y? Closure of Y denoted by Y bar, and this is by definition is the smallest closed set, closed subset which contains Y. That means what? Whenever you use the smallest, that means it is intersection of all those closed subsets which contain Y. So, Y is contained in Z, this is intersection of Z, this is closed in X. So, obviously, this is all these are closed, therefore, it is closed under arbitrary intersection, and therefore, this is a closed set and it contains Y, therefore, this is the smallest closed set which contain Y. Similarly, what is an interior or what is a neighborhood at a point? So, a subset let Y be a subset in X and small y be an element in Y. So, neighborhood of Y. So, why did I write Y unnecessary? This Y is not needed. So, I will use given element X in X, neighborhood of X. This is by definition. Let me use the word open neighborhood of X. Open neighborhood of a point in X is precisely an open set, open subset U of X which contain X. So, not all open sets, but the open sets which contain the given element X is called an open neighborhood of X. And okay, so these are when do you call a point X to be an interior point of X? So, interior point of, now I have to say interior point of a subset, and we will write down some examples. So, suppose Y is a subset and Y is an element here and not. So, then Y is called an interior point in Y if there exists an open subset U in X with Y belonging to U with Y is contained in U is contained in Y. So, to draw the picture, so here this is Y, this small y, this is a subset Y. So, if I can find a small open set which completely lies in Y, then you call it an interior point. So, for example, if I take this disk, suppose Y is my closed disk. Closed means it contains the boundary also, including this, and I am taking X equal to R2. So, and if I take a point on the boundary here, no matter what small neighborhood I take, it will go out of this Y. So, these boundary points are not interior points, but inside points are interior points, because I can take a small radius open disk which is completely contained there. So, this is not interior point, and this is interior point. Okay, so I do not want to recall too much topology at once, because we will use it and we will recall it when we need it. So, now going back, so we have these two maps VL in one direction, and the other direction we have defined a map IK, and both these maps are what is called inclusion reversing. What does that mean? That means if there is inclusion here between the ideals, then the VL will reverse the inclusion. Similarly, see, IK is defined for any subset. So, if one subset is smaller, then IK will be bigger, because IK is precisely all those polynomials which vanish on the all polynomials vanish on the given subset, that is precisely IK. Now, I want to study the properties of these two maps. I mean, when will these maps will be the inverses of each other, and in the best classical situation we will prove that these maps are inverses of each other. That is what our aim is. But before that, I will need to study little bit more algebra, and the first one, for example, I would like to recall that we have kept pending whether the ideals in the polynomial ring over a field are finitely generated. That means, are they given by finitely many polynomials. This is now very important, because whenever we want to check something is a affine algebraic set, we only have to check for finitely many polynomials. So, for that I would like to study now what are called Noetherian rings, and also I will study the Noetherian modules. So, this is one of the important topics. So, I will start at least, and we will study that first, and we will come back to this topology and algebraic geometry once again. So, I will go back to study. Now, the next topic of study is Noetherian rings and modules. So, now we will keep it pending for our notation that that rings. So, now I will switch back to the earlier arbitrary notation for our commutative ring A. A is a ring and I A is the set of ideals. Then when do you say the ring is Noetherian? Precisely when every ideal is finitely generated. So, we say that A is a Noetherian ring if every ideal in A is finitely generated. That is, every ideal A is of the form we will write like this F1 to Fm for some F1 to Fm elements in A. And our goal is to prove that polynomial ring over a field in finitely many variables is Noetherian, where K is a field. Well, but now first of all, this I want to improve this definition in the sense that it will work for a module also. In a module there is no ideal. So, when do you say a module is Noetherian module? So, one possibility is to say that every submodule of M is finitely generated. That is one possibility. But then when our course will go on, more and more algebra will come in, and then I will have to say when the ring is Artinian. So, I will have to give a equivalent formulations of this ideal finitely generated, if every ideal is finitely generated or not. Alright. So, this is what I want to give equivalent conditions, and also when I want to prove theorems about Noetherian rings, Noetherian modules, etc., I will have to prove theorem twice, but I want to set up a notation and definition in such a way that many theorems about Noetherian, Artinian I can prove it together. Alright. For that I will first recall what is a Noetherian. So, first let us recall, this was little bit confusion in earlier also. So, I would recall formally when I have an ordered set x less equal to ordered set. What does that mean? That means this is a relation on the set x which satisfy three properties, and what were the three properties? Reflexivity, antisymmetry, and transitive. So, this means XX, that means x is less equal to x for all x, for all x. Similarly, if x is less equal to y and y is less equal to x, then x equal to y. This is antisymmetry, this is reflexivity. This is true for all x and y where x less equal to y and y less equal to. Transitivity is x, if x is less equal to y and y is less equal to z, then x is less equal to z, that is the transitivity. And typical example of a ordered set is n with a natural order, or q where this order is now extended from n, or r. All these are ordered sets. And but C there is no order, remember C does not have order. Alright, so this is our ordered set. Normally most of the books will refer to it as a partially ordered set. And also computer science guys will write POSET. But remember, I am not going to use this word partially. I will only keep saying ordered set. And when do you say it? When do you say the set is totally ordered? That means any two elements are comparable. Given x and y, x is either less equal to y or y is less equal to x. So, now what is well ordered? So, totally ordered we have defined. The totally ordered means comparability. That means for all x, y in x, either x is less equal to y or y is less equal to x, either or. Well order, that is means every non-empty subset y of x has a maximal, has the maximum, has the minimum. That means there exists an element y naught in y such that y naught is less equal to y for every y in y. So, typically n this, one of the axioms says that n is well ordered. That means any non-empty subset of n has the minimum. This is also called minimal principle or well ordering principle. Now, you see if you look at this ordered set z less equal to, this is ordered set, this is also totally ordered, but not well ordered. Simply because if you take the negative integers, that does not have minimum, you can keep going on the negative side as long as one want. So, it is not well ordered. Alright, so there are not well ordered set, or even Q or R, they are not well ordered set, they are all totally ordered, not well ordered. And remember, when we use John's lemma also I have used the term inductively ordered. What was inductively ordered? That means ordered set in which every chain, non-empty chain, has an upper bound, then you call that set to be inductively ordered. So, this means X ordered set in which every non-empty chain Y has an upper bound. Now, what is a non-empty? Non-empty is okay. Chain is what? Chain is a totally ordered subset of X. This is a totally ordered subset of X, and this upper bound means it is an element which is bigger than equal to every element in Y, but that element may not be in Y. So, for example, if you take X equal to R with the usual order, and if you take Y equal to the open interval 0 1, 1 is an upper bound. 1 is an upper bound for Y in X. So, upper bound in X you should say. So, say like upper bound you have a lower bound also, 0 is a lower bound or minus 1 is a lower bound and so on. See, most of these language is very clearer if you use it correctly. Now, I want to define two kinds of sets, two kinds of more ordered set. So, what was well ordered? Well ordered was every non-empty subset has a minimum. Now, I want to define what is Noetherian ordered and Artinian ordered. And Noetherian ordered should be every non-empty subset has a maximal element, not I am not saying the maximum, but a maximal element. Similarly, I will say Artinian is ordered set in which every non-empty subset has a minimal element. Now, there could be many, and now I will study these basic properties of these Noetherian and Artinian in the beginning of the next lecture, and we will use this language to prove that the polynomial ring over a Noetherian ring is again a Noetherian. In particular, for a field, if K is a field, K polynomial in one variable is Noetherian, and keep repeated use of the theorem I said, we will conclude that polynomial ring over a Noetherian ring in finitely many variables is also Noetherian. And then we will study also modules at the same time. So, with this I will conclude this lecture, and then we will continue our next lecture starting from the study of Noetherian and Artinian ordered sets, and use this terminology to prove theorems about Noetherian modules and Artinian modules, and you will see we only have to prove only one theorem and the other theorem will come like a dual. So, we will with this language our job of proving theorems in Noetherian and Artinian will reduce to the half. So, that is the advantage of this language. Okay, so, with this I will stop and we will continue in the next lecture. Thank you.